in much the same way that equal signs do, except instead of saying the two numbers are equal, they're telling us that one is greater or less than. So if we have something like x is greater than 4, there's several ways we can represent this. So this set is the set of all real numbers greater than 4. So the x just represents some number in the set. So they're saying if x is some number in the set we're talking about, then x has to be greater than 4. Notice that we're using what we call a strict inequality, so there's no or equal to. We have to do that here because we want to get infinitely close to the number 4, but not actually include 4 in our set. So like we couldn't say x is greater than or equal to 5 and have it be the same set, or even x is greater than or equal to like 4.1, because 4.000000000000001 is in that set, right, because it's greater than 4. So we use that strict inequality because it allows us to include every single number infinitely close to 4, but not actually equal to 4. We can also represent this set using a number line. Zero, 1, 2, 3, 4, 6. So probably, all right, have you guys used like the open points and close points, or have you used brackets? So most people see the open and close points first. So we would use an open point here at 4 to show that we're not including 4, and then we shade everything to the right because larger numbers are to the right on the number line. So the open and close points are fine. We're actually going to use a different notation only because it relates a little bit better to interval notation. And that is using hard and soft brackets. So a soft bracket is like a parenthesis. And so it would look like this. So we use what we call soft brackets for those strict inequalities. And then we'll use what we call hard brackets, which are just like the square brackets, for the less than or equal to and greater than or equal to variety. And then the one we'll use the most often is called interval notation. In general, interval notation looks kind of like an ordered pair. It's the smallest number that's in the set, and then a comma, and then the largest number in the set. And then we use those same brackets, so either the soft brackets or the hard brackets, on each side to indicate if that's included or not. So if the smallest number in the set is not included, we would use a soft bracket on the left. If it is included, we would use a hard bracket on the left. If the largest number in the set is not included, we would use a soft bracket on the right. If it is included, we'd use a hard bracket on the right. So they don't have to be the same. Those brackets just tell us if it's a less than or equal to or a strict inequality. What's up, Sam? Good? So in this case, the smallest number in this set is 4. That's our endpoint. But it's not included, and so we use that soft bracket. And then that arrow goes all the way to the right, so there is no largest number in the set. And when that's the case, we use infinity to indicate that this set keeps going up and never ever stops. There's no largest number. And then we always use a soft bracket at infinity because it's not a number that like x can be equal to, right? It's like a concept. Make sense? Okay, there's one other notation. It's called set builder notation. You might see this, like, as far as how sets are given. I won't expect you to write this, because in this setting, it's really kind of silly to use set builder notation, but they introduce it here just so you guys get familiar with it. So in set builder notation, we use the curly brackets, then we say X, and you draw a line, and then you list the properties that X has to satisfy. So this is read X such that, so that straight line is the such that symbol. X is greater than 4. So like I said, in this setting, it's a little bit silly to use this notation because it's just as easy to just write X is greater than 4, like write that inequality, right? So where we use set builder notation predominantly is like when we have more than one property that we want X to satisfy. So if we want X to be greater than 4 and even and it's positive, it's greater than 4. So if we want X to be greater than 4 and even, then we could be like X such that X is greater than 4, comma, X is even. So you can list more than one property of X in that set builder notation. And so it comes in handy in situations like that, or when there's more than one variable. So if you have like ordered pairs, you can be like X, Y, Z such that X satisfies one property, Y satisfies another property, and Z satisfies a third property. So in that setting, you'll end up seeing this set builder notation a lot later on. But for our purposes right now, since we have a single variable and all we're doing is saying it's greater than or equal or less than or equal to something, it's just as easy to use just the inequality. But you might see it given this way, so I just wanted you to be able to recognize it when you see it. So far, so good? Okay, let's do a couple more of these. So this is what we call a compound inequality, which really just means it's two inequalities in one. So if I were to take this away, we would get the inequality 3 is less than or equal to x, which means that x is greater than or equal to 3. And if I were to take this guy away, we get the inequality x is less than 9. So when we do a compound inequality, we're just saying that x satisfies both of those. And it's sort of simple because x is between 3 and 9, and that's exactly what this means. The inequality means is that x is between 3 and 9. So on a number line, I can't draw a straight line to save my life, just so you know. It'll happen over and over again. So let's say this is 3, 4, 5, 6, 7, 8, 9. So 3 is our smallest number in the set, and it's included because we have that or equals to. So we'll use a hard bracket there. And then 9 is the largest number in our set, and it's not included because that's a strict inequality. There's no line there. And so we use a soft bracket there. And then the numbers in my set are all the numbers between those two endpoints. So we shade everything in between. And you can kind of see from this how it lends itself nicely to going from here to interval notation, because those brackets are exactly the brackets you'll use in interval notation. So in interval notation, it's the smallest number to the largest number. So if you ever find yourself having trouble writing it in interval notation, it's often a big help to graph it, because then you can kind of go straight from the graph to interval notation, right? Using the same brackets, the same numbers, everything. Okay, you guys try this one. Do x is less than or equal to 5. And go ahead and graph it, and then also write it in interval notation. Daniel. Yeah. You go by Dan.
Yeah.
Okay, so on the number line, should I use a hard bracket or a soft bracket? Good. 1, 2, 3, 4, 5. So hard bracket, and then should I shade left or right? Left, good. So hard bracket at 5, shade to the left. If your variable is on the left side of your inequality, then the inequality symbol always points the direction you should shade. So like here I have my x on the left side, and my inequality symbol points left. So that's how I know I can shade left. That is not true if your variable is on the right side. So if it's on the right side, what I usually do when I get an inequality like this is I just switch it. So like flip the entire thing over, right? Saying that 4 is less than or equal to x is the same as saying that x is greater than or equal to 4. And then it's a little bit easier to figure out where you're shading. And then, is there a smallest element in this set? There's not, right? It goes all the way down. And when that's the case, we use negative infinity just to indicate that we're going all the way in the negative direction. And then is there a largest element of the set? Yeah, it's 5, good. And then we use a hard bracket there because it's included. Good? Does this make sense? Notice that in interval notation, there's never a variable in there, right? It's always just the numbers. So, I mean, technically, if we were getting really mathy, we would write this set like this. It means x is in this set, but I won't make you guys do that yet. We'll just give this up. Okay, so let's talk solving some inequalities. So what we have so far, these inequalities are going to end up being like the solutions when we solve inequalities. So one difference between solving inequalities and solving equations is that when we solve equations, we get x is equal to like one number. Whereas when you solve an inequality, your solution is a solution set. It's an infinite number of values, right? So it's all the numbers that are less than 5 would make the inequality true, as opposed to just x equals 5. I mean, if that was the solution. One other difference when we solve inequalities, solving inequalities. So you're going to solve just like you solve equations. Except one difference. If at any point you multiply or divide both sides by a negative number, then the direction of the inequality symbol reverses. And that just has to do with the fact that negative numbers are like mirrored across 0 from positive numbers. So if I have something like 3 is less than 7. That means that 7 is further to the right than 3, right? But if I multiply by, say, -1 on both sides and relate the numbers -3 and -7, well, if 7 is further to the right than 3, that means -7 is going to be further to the left than -3. And so that means it's going to be smaller. So when we change those signs, we're kind of flipping all the way across the number line. And so that flips our inequality as well. So let's do 4x plus 9 is greater than or equal to 3x plus 2. So again, the process here is exactly the same as when we solve equations. You want to carry that inequality sign with you the whole way. Like, you don't want to change it to an equal sign or anything. Just keep the inequality as it is. So we'll subtract 3x from both sides, which gets us x. Wait, I have to make a change. I'm sorry. That's not going to do exactly what I want. Make that a 2. Otherwise, I don't get to divide. Okay, we're going to subtract 2x from both sides. And we get 2x plus 9 is greater than or equal to 2. And then we'll subtract 9 from both sides, which gives us 2x is greater than or equal to -7. And then we're going to divide both sides by 2. Now notice, even though there's a negative on the right side, the number that I'm going to divide by is positive, right? I'm dividing by +2. So even though there's a negative number involved, we don't switch the direction of that inequality symbol unless the number we divide by is negative. So here we divide by a +2. Yes?
Are you going to want us to leave this as a fraction on the board?
Uh-huh. So in this case, you could write it as a decimal because it's a terminating decimal, right? If you put that in your calculator, it doesn't go on forever. It like actually stops, and that would be fine. However, in general, I always just leave them as fractions because maybe I don't know which is going to be a terminating decimal and which one's going to go forever ahead of time. In my math lab, it will always tell you if it wants a decimal or a fraction. That can be a little frustrating when you put like a decimal in and it wanted a fraction. But it says right underneath like the answer box, like enter an integer or fraction or something like that to help you. Make sense? Let's write this in interval notation. So our solution set is everything bigger than -7/2. So -7/2 is the smallest element of my set, which I'm including because of that or equal to. And then there is no largest element, and so we just use infinity. If you find yourself having trouble with like which direction to go, just go ahead and graph it on the number line like we were doing before, because that can be really helpful just in seeing it and visualizing. Good? Shall we do another? How about 4x minus 1 is equal to, no, not 5x, 9x minus 11. You guys give that one a try. So once you're done solving, go ahead and write your solution in interval notation. And 24/1. And remember that whole, like, the 2/3 times 1 minus 4x, that's all one term. And so we multiply by 24 just once, right? So we'll multiply 24 by 2/3, which gives us 16 And then the 1 minus 4x just stays the same. And then 15, and what is that, like 3? And then we'll distribute that 16 in combined like terms, which should give us 1 minus 64x. I skipped a step, but everybody got to that point. And then subtract 1 from both sides and divide both sides by negative 64, so that flips my inequality symbol. This is negative 2 over negative 64. No, this is positive 2, I'm sorry. It's the second time I've done that today. And so x is greater than negative 1 over 32. If you were going to graph this, like, it's a little funny because it's a fraction, right? You don't have to, like, mark out, like, 30 seconds perfectly. You can just be like, okay, here's 0, and here's 1. And 1 32nd is way closer to 0 than it is to 1, right? So I'd maybe do, like, right here. And then your shading. So it doesn't have to be perfect. It just has to be around the correct place. Sorry, that's negative 1. And then in interval notation, the smallest element is negative 1 over 32, and then we go up to infinity. You guys feel good about this? Mm-hmm. The inequality stuff? I wanted to take just a couple minutes to talk a little bit more about percents from the other day, just to go over. We kind of had to rush through like that last problem, so I thought we'd do one more like it. Does that seem like it might be beneficial?